right, here we go with the second part of the acid-base discussion. Okay, so I don't think that this actually recorded, but what I had said earlier was that this is where we start talking about this equilibrium, and HF might you might consider that as a strong acid, except that this F minus is actually a little too strong for its own good, and it actually pushes things in this direction. So it's a binary acid, and it's one of the halogen acids that's soluble, and in that case, they're usually strong acids, but that's the explanation for HF. So again, the difference is the strong acid, there's a weak attraction between H plus and A minus, um, and so that results in complete ionization. But the weak acid, there's not as much, and so I'm sorry, there's a little bit stronger attraction between H plus and A minus, and so there's this partial ionization that occurs. So here are some of the weak acids that we're going to include in our discussion, right? Hydrofluoric, we explained that, acetic, um, carbonic, phosphoric, sulfurous, and formic acid are all weak acids. Here's a table of weak acids, and in this table we have something that is the ionization constant, right? Each one of these now has what we call a Ka, right? And you know what a K is, right? It is an equilibrium constant. The A just means it is the acid dissociation constant or ionization constant, okay? And the size of this matters, and the size of this means how far it goes towards products, right? So how much it dissociates, okay? So the bigger it is, the more it dissociates. The smaller it is, the less it dissociates. So this is basically a stronger weak acid at the top here and a weaker weak acid at the bottom. Remember the discussion that we just had about water acting as both an acid and a base. When water is in when water is part of an acidic ionization, it acts as a base. When it's part of a basic ionization, it acts as an acid. Okay, so now we're back to the ice table, right? This is where we would have a Ka, right? And if we said what the size of that Ka was, then we could go ahead and describe this as an equilibrium. And so this Ka would equal the H plus concentration times the A minus concentration over the HA concentration, and you would get something that looks like this, and we would solve it, right? In this case, we would have an x squared involved, and so we would have a quadratic. So if we consider this and say, okay, this is HCN, well, again, this is just an HA, right? And it is going to an H plus or an H3O plus and an A minus. And so this is um, plus X and minus X, right? And so this becomes 0.100 minus X, X, and X. And if we put this into the Ka expression, Ka is equal to x squared over 0.1 minus x, right? And we could solve that and come up with um, an answer. Okay, here is the equilibrium condition. So again, you saw that table earlier where there were KAs for all these. That's where you would look this stuff up. So again, HA going to H plus and A minus, and minus x plus x plus x, and this becomes x, x, 0.200 minus x. And then we're ready to solve. Here it is. Take a second or two and think about this one. It's going to look awfully like the last ones that we've talked about. And there's the solution, right, that you would then plug into the equilibrium expression. So let's talk Ka, right? How can a Ka be determined? So if we know the concentration of the acid to begin with, and we know that it is HA, right, going to H plus and A minus, right, and we know that the concentration of H3O plus through finding the pH, right, if we know the pH, we can find the H3O plus concentration. We know that it is 5.6 times 10 to the minus fifth, and we know that this is plus x, and this is plus x, and this is minus x, and this is 0.100 minus x. Guess what x is? Okay, x is 5.6 times 10 to the minus fifth. So now I know what x is. I can plug that into an expression and say Ka is equal to 5.6 times 10 to the minus fifth squared, right, because it is the same for both, and that's over 0.100 minus 5.6 times 10 to the minus fifth. Okay, and then we could solve that for Ka. So here it is solved, right? You can make this approximation because 5.6 times 10 to the minus fifth is so small that even if you plug that in and subtract it from 0.1, you're going to get a rounded number that is 0.1, 0.100 actually, right? And so just plug that one in as the concentration of HA, and then these are the concentrations for H3O plus and A minus, and you get 3.1 times 10 to the minus eighth. So an interesting part of this is that the amount of dissociation actually is going to depend on the initial concentration, right? So we'll work through that. So the more concentrated it is, the more it's going to go towards products, right? So if we look at this HNO2, the fact that we started off with this 2.5 means that there's going to be more on the product side. But more doesn't always translate into a higher percentage. Okay, so in other words, when we started off with this 2.5, we got a larger concentration of OH minus, I'm sorry, of H plus, and so the pH was lower, but the percent dissociation is actually smaller because the amount of H3O plus relative to the original is smaller. Okay, so percent dissociation means how much of this is generated with respect to this, right? And at a lower concentration of 0.2, you get less in terms of the amount of H3O plus compared to 2.5, but a larger percent is dissociated. So we can look at this a little bit with HF. Again, your Ka is going to be equal to x squared over 0.150 minus x. Before we start talking about weak bases, let's talk about strong bases real quickly for another second or two. You know it means complete dissociation. You also would recognize that these bases that are these hydroxys that are soluble, right? Lithium, sodium, potassium, strontium, calcium, barium hydroxide, all these are soluble hydroxides. And if they're soluble, they go completely, meaning that they're going to completely generate as much OH minus as they can. But a weak base does not completely go there, right? And a weak base is something like ammonia. And we looked at this before with NH3, right, in water, and it goes to NH4 plus and generates OH minus. So that's a weak base. You got this equilibrium, right? Same thing that we were just discussing with the acids, weak acids. So in general, amine bases are weak bases, and they protonate, meaning that they take on an extra proton on the amine group, and they all behave very similarly. So you've got ammonia, and then you've got this methylamine in this slide. So common weak bases you've probably heard of. I discussed carbonate before. From the other direction, the carbonic acid and oceans and dissolution of CO2 into the oceans and how that's making it more acidic. The carbonate, then CO3, is actually part of coral reefs and shells, which means that it goes in this direction as you add more as the carbonate, right, concentration increases, and so you have dissolution. Methylamine, ethylamine, ammonia, these are all amines, right? Amine, and we already talked about the fact that most amines are, or this is actually not an amine, it's not an amine, it's an imine, and that means that it only has, it doesn't have two hydrogens on the end of it necessarily. Anyway, if it's a nitrogen containing organic compound, it is generally a base and a weak base. Here are pictures of these three: ammonia, methylamine, pyridine, and what you see is that lone pair of electrons, and that's what's important in their basicity. Can do the same thing with ice tables, right? Minus x, plus x, plus x, right? And then that becomes 0.100 minus x, x, and x. And now if we have something that we describe as a Kb, the Kb is equal to NH4 plus concentration times OH minus concentration over NH3 concentration. Okay, so here it is solved on the slide. Okay, so I'm going to stop here, and we're going to go ahead and I'll pick it up and try to finish a third part later today, and then I might even break that into a fourth part so that you guys aren't in this quite as long. Okay, so this is the first part of part 2.